Greetings. Welcome to our first presentation on masonry. It's going to be a pretty thorough review of different types of masonry units, how these different units and bricks are put together, used together as modules to create walls, and mortar and grout. Suffice to say that stone and masonry are the strongest and most durable of all pre-industrial building materials. A lot of buildings, this is the reason why so many buildings from antiquity have survived, because they were built from masonry. This beautiful image here is of Lion Gate, the Lion Gate in south of France. Measures 10 feet tall, 10 feet wide at the base here, and just at the lintel about 9 feet. These two vertical pieces are leaning in a little bit. And originally I think there were double doors on this, which is really very striking, but beautiful just the way it is there. So there are a lot of slides to cover, so I'm going to move along pretty quickly. Some of them I'm going to have a little less to comment on. So a little different. We have at least a good dozen slides here. We're just going to take a quick tour of some masonry installations, actually. And so stone, going back to antiquity again, the pyramids, the Parthenon, the Pantheon, of course. There's also concrete in there, poured concrete for the ceiling. And then we also have viaducts, and these are the great Gothic cathedrals, probably dating to around the 11th, 12th, 10th century, perhaps. And so that was stone, and now this is brick here, also dating back. The oldest discovered bricks date back to about 7500 BC in the Middle East, actually. Mud brick, similar to this. It's ubiquitous. It's everywhere. Here in Philadelphia, very, very common for early colonial architecture. A lot of striking buildings like this in the area. Here in Boston, this is the public library in Boston. So points out that stone was used on the main facade, but brick around back in the interior courtyard, not visible from the street. Here some of Gary's work still, so brick is still very relevant, still being used. I'm not particularly a big fan of Gary's myself. I did see a beautiful bank of his in Berlin, gorgeous woodwork inside and a lot of glass. But this is not really my type of thing, but not really the point. This is much more to my taste. These are actually, I got to tour this building here at University of Pennsylvania. So this is Williams and Senn Architects. If you're not familiar with their work, you should definitely look them up. Absolutely beautiful, beautiful pieces. The Barnes Museum here in Philadelphia, the Folk Art Museum in New York, which no longer exists. And so this is a lab at the University of Pennsylvania here. What I just read, I'm just going to read to you here quickly. While most of the buildings on Penn's campus are steel construction with red brick cladding, Skirkanich Hall is a concrete building with a shingled glass and aluminum curtain wall. It's kind of these kind of fish scales, kind of. So shingled glass and aluminum curtain wall, zinc panels we'll see inside, and glazed green brick. So very different, really very striking, a gorgeous building. A lot of great work from these architects you should get to know. So very, very bold, different color there, the green. And then here we are inside. So this would be like a tile. This is similar to what we saw on the timber frame residence, the project that I had worked on, and we saw the brick masonry going up in between the timbers on the exterior. So thin tiles, very striking again. Also, to my taste, the work of Louis Kahn, big here in Philadelphia as well. So here we are at the, again, on the campus of Penn, so the Richards Medical Building, very striking, very, kind of an industrial look to it. I'm a big fan of Kahn. Here, two more projects by Kahn, the Indian Institute of Management, a beautiful, striking building. I believe this was towards the very end of his life, I believe. And Phillips Exeter Library, another striking building. If you've never seen interiors of that, you should take a look as well. Gorgeous concrete and wood. Oh, yes, and then I just wanted to note here, I'm just going to adjust this frame a little bit. There we go. Also note here on YouTube, My Architect, A Son's Journey. It's a film. If you haven't seen it, you really should. I was surprised to see the whole film is actually on YouTube. A really great great movie. It's made by his son, and Kahn had a very challenging personal life, let's say. And so the son is kind of tracing his journey through each of Kahn's buildings, and they end up, towards the end, it ends up in India. But it's a very personal look at Kahn's life, but it's also a tour of all of his buildings. It's a wonderful movie that you should check out. Okay, a few more here by Office DA. I'm not familiar with them, but some of these slides I inherited from other instructors, and some are from the book, the textbook, obviously. But I find this to be quite striking. So a couple of slides coming up now, some more expressive uses with masonry, but very sharp looking, I think. This I also really like here, where it's actually used as a screen. Looks very delicate. So these kind of columns of brick are being held in place here by these horizontals beyond, but looks very delicate, very striking. A couple more around window details, very nice. And finally, one last look at Peter Zumthor, if you're not familiar with his work, the Columba Museum. So this was I'll just read a quick piece to you. So the site, originally occupied by the Romanesque Church of St. Columba, was destroyed in World War II, and it was replaced by a chapel later. So now here, the new structure, Zumthor, built for the museum, now shares its site with the ruins of a Gothic church and the 1950s chapel, wrapping a perforated gray brick facade like a cloak around both the museum and the old church. So go inside, we could see. So here's the original ruins, and then these gray bricks with this kind of perforated wall is what Zumthor kind of wrapped those existing ruins in. Very, very striking. If you're not familiar with Peter Zumthor's work, I intend to show some more of it. Beautiful, beautiful projects. So it's just incredible to see what can be done with these materials in the hands of such a master as Zumthor. Beautiful, beautiful piece. Okay, all right, getting into the nuts and bolts now, the advantages and the disadvantages. So bricks are modular. They could be combined in a lot of ways. We'll be looking at that. They are non-combustible, so that's good. They don't need painting. I've seen painted bricks before. It usually doesn't last that well. They do have a lot of moisture. They retain moisture, so they don't paint very well. I more often see poorly painted or failing painted walls, brick walls. Very durable in general, and increase the thermal mass of a building. So the thermal mass, that's what's going to hold the heat or hold the cold. So it holds on to those temperatures, which could be a good thing. Disadvantages, so it does degrade. The freeze-thaw cycle is damaging to it. It's very heavy, so it needs a robust foundation, and it requires skilled labor, and it does not lend itself well to mechanization. So labor intensive, skilled labor. Okay, so I was reviewing all of these different slides from the various sources that I had, and it kind of jumps around overall the whole presentation, so I just wanted to start up front and talk about the differences between some of these units. So we have clay brick here, we have concrete block, hollow block, and lightweight block, 3 different things. I found this at materialtree.com. And then it's followed by a extensive chart, more extensive than this if you want to take a look at some other properties. But basically it has other names that these pieces are known by. The composition, which we'll be talking about, so some of them involve clay, the terracotta ones, the bricks and the hollow blocks involve clay, which leads to its reddish appearance, and the concrete, obviously, cement and aggregates. And then it talks a little bit about weight, so I do not know the metric system, but basically, regardless, it looks like here a 4-inch solid block here weighs in at about 17 or 18 kilograms, and here the hollow weighs in at about 6 or 7, so less than half or close to a third of the weight. So a lot of weight is saved here in the hollow block. And then here we have the lightweight block made up of, or coming in at about half of that of the concrete block. So we're going to be talking about bricks, which I will call bricks, and then we're also going to be talking about other masonry units. So CMU is a concrete masonry unit. So those other units, I would say when I refer to CMU, I'm really kind of talking more about these pieces, as opposed to kind of the the classic bricks. Okay, moving on. So masonry units, there are different types: bricks, blocks, stone, and other. So cut stone, that's a different animal that we will get into in the next presentation. Here and also we have natural stone as well, again a different animal. We're again really talking about modular bricks and CMU units, because the two share a lot of properties, and a lot of things that are pertinent to one material are also relative to the other. Okay, we'll take a quick cut over to YouTube and let's get a visual. The extruded bricks being cut into individual units here. Okay, so that was version number 1, brick forming number 1, and then we'll jump forward a slide, and now we're on to number 2, the second way to get this done. So soft mud process, so moist clay is pressed into individual molds here, and there's also a dry press process where they're machine pressed into molds at high pressure. So this is a different process from the first. They're actually molded here, and the result is more natural variation in texture and dimensional uniformity than extruded bricks. So there's more variation in the amount of uniformity, so they are not as uniform, and they cost more typically. And after that process, then the bricks are fired, put into kilns. There's different types of kilns, 10 to 40 hours. Not going to dig into the details of that. And then there are also many special sizes and shapes for all different applications here. So custom shaped bricks can be used to form arches, water tables, sills, and many other. So sills we see here, sills underneath the window. The water table, that's a detail that happens around waist height on a building, kind of. It would be a little step like that. If this wall continued up kind of behind it, I might call that a water table. Otherwise, I don't really see one there. These all just kind of look like parapets or just short knee walls to me. But suffice to say, there are bricks are manufactured for all different applications and locations. All right, and then also, so here, this what we're talking about. This would be our CMU. So what do they call it here? Oh, so this is a glazed block. Yes. So again, concrete masonry units, but here with a glazed surface on the front. This is something you probably see in, like, I'm thinking about like high school gymnasiums, things like that, where you need something very durable, but you want to have it finished. And then terracotta, so that's our common bricks, and then also glass block falls into this category. Masons would be the ones to install glass block as well. All right, moving on. So these are the red bricks again. So clay or shale is what makes these up. So the type of shale or clay, the plasticity of the mix, the pressure under which the material is forced, all contribute to the character of each individual brick. So here we see some hollow bricks being put in, and then there are various others here. A lot of variety in the look. Okay, moving on to brick sizes. So this is important. This is all about how they work so well as modules. So in general, there's a nominal and an actual, again, just like our dimensional lumber. So here the nominal, so we'd say it's 4 by 8 when what it actually is 3 5/8 or 3.5 by 7 5/8 or 7.5. So again, manufacturer to manufacturer, there's a great amount of variety out there. The designer should be specifying exactly what they had in mind when they're using it. And then also it goes on to say here is that the joint thickness between the bricks also varies. Okay, so here we see 4 inches in width. So the 4 inches in width is actually 3 5/8, and then it includes that that bed of mortar. So the 3 5/8 plus the 3/8 equals the 4. So one brick plus that mortar bed, that horizontal mortar bed there, would equal the 4 inches. Okay? And then in the vertical direction, the brick would be 7 5/8, and then it would have a mortar joint at its head here, a vertical mortar joint, and that would be 3/8 for a grand total of the 8-inch length. 7 5/8 plus the 3/8 would gives us the 8, or the 7 1/2 plus the half gives us the 8. Okay, moving on. So classification to point out here. So hollow brick, what is it? It's up to 60% void. So obviously results in a lighter brick. Takes less energy to fire. So a sustainable issue, a positive. And then very importantly, those hollows can accommodate steel reinforcing. We're not going to talk too. We'll get into the failure, some brick failure modes later. But in general, brick is very strong in compression. That means one could rest on the other. But it has very little tensile strength. So that's why steel reinforcement is used to provide more tensile strength. All right, different brick types. All right, so common building brick. So this is something where appearance is not a requirement, typically used as a backing material. So this is for interior partitions in basements of buildings, perhaps, where we don't care about the appearance at all. So that would be a building brick or a common brick. Facing brick, that's when we do care about appearance, so it's in a finished area, obviously. Hollow brick is facing brick. Anchored veneer, used as facing brick in anchored veneer. May contain steel reinforcement and grout as well. And we're going to take a good look at the use of hollow brick and how it is reinforced. So that'll be in our second presentation. Thin brick, so that's what we were talking about there, the hall. This is kind of used more as a veneer. So it kind of looks like brick, but it's actually not. It's much more like tile in your bathroom, kind of pasted to the wall. Paving brick, so this is used on horizontal surfaces for pedestrian or vehicular use. Glazed, so that has the ceramic finish. So that was also the green brick on the hall there at the UPenn lab. It's also glazed, the green. And then fire brick. So this is usable for high heat, obviously, furnaces and fireplaces. So a lot of different types. Okay, so moving back on, I'm just going to jump back real quick. So here we are with facing brick again. So this is when appearance is a major concern, and then there are 3 classifications for that. Jump back down here. So facing brick, so appearance characteristics graded for exposed applications, so very little variation here. General purpose face brick for, again, so this is going back to where it is not a concern. And then here, great non-uniformity in shape and size. So 3 different grades or classifications for this common brick application. Okay, another way to grade bricks is by the durability, which is defined by its compressive strength. I mentioned that it's very strong in compression. Absorption, so how much or little moisture it's prone to absorbing. And then the freeze-thaw cycle, so how well it could resist that. So this is all concerned with durability. And then here, these different grades, SW, MW, and NW, points out. So here, SW, so this would be our coldest region in North America. So any weathering region above or below grade. So this is our most durable grade, the SW grade. So it can be used below grade, so that's another important characteristic that has to be pointed out where it's going to be used. So below grade in any region is possible in our coldest of regions. Here, only above grade and in regions that are not as, where the weather and the cold are not as intense. So here we see in the Midwest and coming in lower in the southern states. And then finally, the very, very most southern states, or the most southern part of our most southern states, interior brick. So concealed building brick, so this is inside, not exposed to the weather. So our most mild grade in terms of durability. Okay, so now we're going to jump into just a little bit about, specifically about the concrete masonry units, or CMUs as I call them. So manufactured in a great number of varieties, shapes, and sizes. So, something for everyone out there. All right, so different ways to classify them. So this first point is on weight, and the next slide is on a couple other ones. So weight standards applicable to CMU contain 3 different classifications for weight based on the pounds per cubic foot. So there's normal, medium, and light weight. So normal weight comes in at about 125 pounds per cubic foot or over. Medium is less than that, 105 to 125, so structural types and sizes are stocked here, so this is their most commonly used. And then lightweight comes in at 105 pounds or less. So lightweight is the most expensive. Okay. So medium weight, the most popular, the greatest availability, used for structural applications, moderate weight and cost generally offer the best labor production material ratio. So this is typically what builders prefer to use. Here is our medium weight. Okay, so that's the weight. Then we also strength. So again, these are manufactured, and structural engineers specify exactly what the compressive strength should be. So that should always be on the radar of the contractor who's ordering the material and installing it. So the compressive strength is one issue. And typically the compressive strength comes in at about 3,000 psi, so similar to concrete precast or poured in place. Similar. Shape, basically we're talking about solid or hollow with voids. And we're going to take a good look at these in particular and why they're used and how they're reinforced. Sorry about that. And then permeability. So again, where is it exposed and where is it relative to grade? Okay. So again, just like bricks that we just looked at, so there's a nominal and an actual size. So 4 inches is actually 3 5/8, and then again, this particular split face wouldn't really have it might, but typically not have a mortar joint behind it. But going in the other directions, for instance, so this would be a 16-inch block, actually 5 5/8, and then the other 3/8 make up the vertical mortar joint. Okay, so again, a lot of variation, lots of different pieces out there. Okay, moving on into terminology now. So this is moving into really bricks as modules, so putting them together to create walls. All right, so a course, one horizontal row of bricks. So you definitely have to be familiar with this terminology. So this would be one course, horizontal bricks lying here. A bed joint is the horizontal joint, so that's right here, the white joint. So one, you would say that one brick is accompanied, well, I guess it's kind of bookended with two bed joints, top and bottom. And then also likewise head joints, that's the vertical ones. So same, one brick is kind of bookended by 2 vertical head joints. All right, now we're looking at, in cross-section, looking at a wall that has 2 widths. So a width is 1 vertical stack of bricks, so this is a single width, and this would be called a double width wall. So it has 1 width and 2 width. And then the joint that brings them together where they meet is called the collar joint. So that exists behind the brick wall, where, just jumping back here, this is the exposed brick wall, and this is everything that we see. We see bed joints and head joints. We do not see the collar joints. They are behind the wall. All right, so different names for how they're positioned. So again, this is a double width wall. So this is the first width that's exposed, assuming that we're out here, and this is the face. And then this is the width that would be behind. So here we have stretchers. So they are laid down horizontally, and we see the face, the horizontal face right here. Or headers, where they are laid down, and the end of the brick is shown to us. All right, and then these are used to lock in and keep these 2 widths joined together. So these are serving a structural purpose, holding holding the double width together. Here we see soldiers, so again we see the long face being exposed, and here's a rowlock. So similar here to the header, but standing on edge. So 4 different positions that a brick could lie in. All right. So headers and rowlocks in a multi-width wall, so work together, that they tie those 2 widths together, as I just mentioned. A single width wall, very different, so different brick bonds may be chosen purely for visual patterns. All right, so sometimes here, so if this is a single width wall, this would not be a long brick. This would not be a brick put in this position. This would just be like a half a brick, and it's only there for aesthetics, no other reason, if this is in fact a single width wall. Here in the double width wall, it isn't a full brick, and they are serving a very important purpose. All right, so moving on to brick bonds. So again, these brick bonds apply for both single width and double width walls. So here, running bonds. So this is all stretchers. This is our most common, simplest. So that's all we have in there. Obviously, the one above is set at the midpoint of this one, and that's how they lock themselves in. So a common bond there, and there are many different bonds. We're just going to look at 2 slides and 4 examples, but there are many different bonds out there. Some more ornate, a lot more ornate than others. So a common bond. So stretcher courses, here we are. Those are our stretcher courses with a header row, usually every 5 or 6 courses. So right here, that's our header row. And then you would expect another header row to be 1, 2, 3, 4, 5 coming in right about here off the picture. All right, English bond, alternating stretcher and header courses. So here, stretcher, header, and so on. Flemish, alternating stretchers and headers in each course. So here we are, stretcher, or double stretcher, so I guess it's 2 stretchers and then a header, 2 stretchers and then a header. So many different varieties, typically chosen for aesthetics, typically. While the headers do serve purpose, I believe the choice of the bond is mostly an aesthetic choice. Okay, so here, again, specified by the structural engineer, the mortar joints. So here, bed joints and the head joints. So come in various sizes. So 3/8 joint is the most common. Sometimes thicker ones and thinner ones are used, again, for aesthetics. Thicker ones are also used for reinforcement. So we will look more into in our next presentation. All right, and then here the engineer is specifying the allowable tolerance, so that all bed joints should be within 1/8 of an inch of each other. And then he or she is a little more liberal with the head joints, saying that they could be within 1/4 to 1/8 to 3/8 of an inch of each other. Okay, moving on. So here we are, getting a better look at the issue of modules. All right, so, and this is very similar to the framing of the stud walls in concept, working with modules, the 16-inch increments or the 2-foot on-center framing modules for studs, that is. All right, so to the greatest extent possible, brick masonry wall dimensions should conform to the brick module to avoid making the tradesmen cut bricks and work with small pieces, which is just not efficient. All right, so here we have 7 bricks coming over with 6 joints shown, and then we turn the corner, and then we have 6 bricks running into an inside corner. We turn, and we have 4 bricks. So this is a very smart layout, no cutting necessary. So, good designers, this is what they should be doing, saving their clients money and not producing waste. All right, and then here, so moving to CMU, same issue. So here we have 3.5 blocks in this direction, showing 3 joints. And then we turn the corner at the outside corner, and we have 3 blocks facing there. So it would be either 3 full blocks, or it would be 2 blocks flanked by half blocks. And you can see how this all gets locked in. And again, nicely here comes a window or something, some sort of an opening, I assume a window. and it is 2 blocks wide. So again, working with the module. Alright, here it is getting put in place. Mortar is identical, so this is specifically talking about CMU. It's the same mortar as used for bricks. Corner leads are laid first, so the corners are located and they are built up like such. String lines and levels are used to keep the walls plumb, so we want this to be plumb. And then we could see strings coming in right here, so the string would be extended to the other corner of the building, and the mason would follow the string, make sure that the block is properly aligned to the string. Joints are tooled, and the face of the blocks are clean as the work progresses, so that would be here. This is the face, so any excessive mortar that gets squeezed out would be knocked off with the trowel. Okay, and again, so here we could see this is earlier. This was probably not put in on the same day, or this is put in earlier at some point, and you can see how it's been cleaned. And then the same will happen with this. Before it is dry, it will be struck off with the trowel. And here he appears to be holding probably a 4-foot level, making sure that this wall is plumb on the outside. All right. Here, going back to the dimensions. So note the modular layout of the concrete masonry on either side of the door opening. So here, this would be the pier, referring to this kind of column as a pier. So it is 1.5 cinder blocks. So that would be 16 inches plus 8. So that's a 24-inch pier. And then on the right, it points out 32 inches. So that's 2 blocks. 1 block, 2 block, and then I don't know if that's a window or out an outside corner, but that's 32. So either 2 full blocks or 1 flanked by 2 halves. So again, a smart layout, no waste. All right, a couple of other architectural terms. So here we are spanning openings. So a lintel spans an opening over in a brick wall. So that could be precast concrete, which is what we see there most likely. An angle iron, so that would be steel, could actually be stone, or it could be reinforced brick, and we'll see some more details of lintels in our next presentation. Also, traditional arches, very attractive. This would be built with false work, so there would be wood put into this before the windows placed, and then the brick would be put in place. After it's dried, the wood would be taken out. And here's corbelling. So these are kind of cantilevered bricks, so different ways to address openings. Okay, moving on to the final section of this presentation, mortar and grout. So 2 different materials, all right? Mortar and grout, both used in masonry and tile work, but serve different purposes. They're both made up of Portland cement, which makes them harden, and their variables include the aggregates that are added to them, as well as the amount of water that's added. So here, I just pulled from arctoolbox.com, and I struck out the word stick. It says here, mortar, the role of mortar is to make materials stick to one another. When I teach structural engineering to our construction or architecture students, I always point out that the mortar really has no real structural purpose. It's not glue. It doesn't have any tensile strength. So I do take issue with the word stick. It doesn't really work like that. It's kind of sitting in a bed of it, but it would never hold it together in any. If something were pulling 2 pieces apart, the mortar would never hold it together. So it's not really like a glue. Yeah, so that's the mortar, which we were discussing. That it's the bed of mortar that a brick would sit in, essentially. Grout, different. So this is a filler product, and it's intended to flow, so it has more water. So we're going to look at our next presentation. We're going to look at details of how hollow CMU is filled with grout for structural purposes. So a person installing tile also uses grout to fill the spaces. So again, going back to the tile floor in the kitchen or the bathroom, after the tile has set and it is hardened in the mortar that it's sitting in, then the mason would come back the next day and grout it, and the grout would fill in between the tiles. All right, moving on. So again, just some differences. So mortar used as to bond masonry together. That's I guess I like the word bond maybe better than stick. It's similar. It's similar, but we'll go with bond, I guess. So composed of cement, sand, lime, and water, and then there are different types of mortar for different uses. So exterior or interior, bearing or not bearing. So grout, similar again, but used for filler in vertically reinforced walls. So that's where we would have rebar running vertically in a wall. Specified as either fine or coarse grained, and it's a filler product. One last time there. All right, moving on. So mortar here cushions the masonry units, ensuring uniform bearing one against the other. Uniform bearing. So it produces a nice uniform bed for the units to sit in. Seals the joints between, minimizing the flow of air and water. Yes, I would definitely agree with that. And then adheres units, providing resistance to lateral forces. So again, adheres bonds or sticks, just realizing that they have no structural tensile strength. I just have to add that. All right, moving on. So mortar in combination with the brick contributes to the appearance of the wall. So there are many, many different appearances out there that could be formed with the two pieces. So here we are looking at some mortar joints. So should be sufficiently plastic, meaning wet and able to be spread, and not flow but spreadable. Units should be placed with sufficient pressure to extrude mortar from the joint and produce a nice tight joint. So intentionally being pushed. So this mortar should be coming out. A little bit should be kind of oozing out when the mason puts some pressure on it, and then it gets cleaned off. All right, here, so talking about the joints, very important issue. So incorrect mortar, not cleaned out to a sufficient uniform depth, so not cleaned nicely. Edges of brick damaged by tool or grinder creates a wider joint. So this is where the masonry wall will be vulnerable to water and air passing through. So this is a poor job. Here, the mortar's cleaned out to a uniform depth of 1 inch. Right there, nothing's damaged. So this is well done here. So, concerned with weather resistance. All right, so a lot of different varieties here. So here we are on the outside face of the wall and looking into it. So here, the execution of joints is very important to achieve the correct structural strength, not to have the walls permeable, and of course, good architects care about what these look like, as do clients. So troweled, any excessive mortar is struck off with a trowel or tooled, a shaping tool, which is what we see here. So just striking it off would leave it just kind of flush, like here. That's what the trowel would leave. And then we see a lot of other variations on the way that it's taken, it's resolved. And we could zoom in here and we could see a little more. So it points out, compacts the joint surface to make it more durable and more water resistant. Important. The appearance again. And here it points out that the concave and the V joints shed the water most effectively. So concave is here and V is here. So the most effective in shedding water. Very, very important. And most resistant to freeze thaw, and therefore most resistant. So a very, very important issue. Not simply just an aesthetic issue. Here, I inherited this slide from somebody else, but I thought it was very interesting, so I left it in. So looking at a Frank Lloyd Wright building, talking about how the horizontal joints have been tooled, but the vertical ones have not. They've only been cleaned off. So it creates these dark shadow lines that are continuous. Very interesting. So obviously lending to his architecture, these long horizontal planes that he wanted to. He's building these houses out on prairies, I suppose, or in prairie-like areas. So wanting to, I guess, accentuate the horizontality of the building. So bringing it down to the level of the how the brick mortar is finished. So. All right, moving on. So the ingredients we discussed: Portland cement here, aggregate, sand, hydrated lime, and water. Right. Okay, on to mortar types. There are various types. I'm not going to read all of this to you. I noted this again. I inherited this slide as well here, but the designation of mortar types in decreasing order of strength come from every other letter in the phrase mason work. So M-S-N-O-K, so kind of funny. Not really necessary to memorize that, or memorize any of this for that matter. So different types for different applications: load-bearing, non-load-bearing, inside, outside, interior, exterior, that is. So moving on, also admixtures. We could add color to mortar, so just aesthetics. All right, characteristics of plastic mortar. So again, this is wet mortar. Should gain enough strength and harden in a reasonable time so that further courses of masonry can be laid without excessive racking moments of courses below. So as often the case, they move along pretty quickly and they start building taller and taller, so it wants to be wet and workable when it goes in at first, but you want it to harden up pretty quickly, because once it has 2, 3, 4, 5 other courses on it, it needs to be firm and not kind of move, not allow any movement. Fresh mortar should have sufficient workability, yes, and it should have the ability to retain water, preventing its escape into the unit. So it should hold its own water, essentially. All right. The stronger the mortar, the less flexible it is, and then it gets more brittle during these freezing and thawing cycles. So we don't want to over-specify. You should not over-specify. And the strength of the mortar is specified relative to the strength of the units. The mortar should always be weaker, so we don't want to over-specify. It's not always a good thing. All right, moving on to grout. So mortar is what was laying in the beds, and now grout is what is filling in the openings, the hollow voids. And this is a demonstration, so they've nicely cut away parts of the block faces and filled it with plastic to show, I guess they're studying and showing off techniques to have a more free-flowing grout, so that it doesn't, so that it fills all of these voids properly. So self-consolidating grout moves freely in the tight spaces, as seen through here, yes. And then they're just talking about new admixtures that are just improving the quality of grouts. Here, this is taken from a slump test where we have a metal cylinder. This is done on site. This is a quality assurance kind of inspection that's done on site. So this cylinder would be filled with concrete mortar or grout, and then the cylinder is pulled away, 12-inch cylinder is pulled away, and then we see how much it sinks, essentially. So concrete you would expect to sink anywhere from 1 to 6 inches, mortar 5 to 8, and grout being the most fluid, sinking 8 to 11. This is a test that's used for consistency, to measure concrete, to make sure that from batch to batch, from truck to truck, it has a consistent slump. Okay, moving on, so let's take a quick look at a detail and how we accommodate. We're going to look at a lot more details in the next presentation, but here we're specifically concerned with how a wall like this would accommodate the grout, or is designed to accommodate the grout. So looking around, so we have bond beams, so we're going to talk about that in the next lecture in more detail. So this U-shaped channel block is put in, the horizontal rebar is added in, and then it is grouted. And it says here, stop the grout 1 inch from the top of the pour to create a shear key. So that shear key would be just like we saw on the top of the footings. So there'd be a little key put in so that the next units could lock into it. So it points out here that this is option 1, is to use a U-block where there is a void, a channel, a trough, essentially. Unit 2 is down here. A standard CMU is used, and the webs, the middle pieces, are knocked out at the bond beam course. So they'll have these bond beams every few courses per the structural engineer's direction. And so he's saying you could either buy these pieces, or you could just knock the webs out and put this mesh down at the bottom so that the grout does not go through and fill in where it should not fill in, essentially. And then we see the vertical reinforcement coming through, and then there are clean outs so that any grout that does fall should be cleaned out at the bottom. Okay, so that is, and then here we have some terminology also. A grout pour versus a grout lift. So the lift is any amount of grout that's placed at one time. So one bond beam could be one lift. The pour, however, is made up of several lifts. However many lifts, one or more, that happen before additional masonry is added. So this could all be built up. There could be one grout lift poured here, and then there could be a second grout lift poured here, and that would make, those two lifts would make up the entire grout pour. And then the masons come back and add more CMU, more courses of CMU. So those are the terminologies. And finally, just a quick image of grouting. And I've heard, don't know from experience, but I've heard that these hoses are very heavy. So this is high lift grouting, filling this wall. Okay, that is masonry units, modules, and mortar and grouting. Thank you.